What if the Big Bang wasn't the very beginning, but just the latest episode in a long cosmic drama? We once thought we knew the story, but new data, more powerful telescopes, and bold ideas are changing everything. The universe likely didn't appear out of nowhere. It might be the child of a black hole, the echo of a much older cosmos, or a sudden expansion of space itself following a massive contraction. Scientists are finally piecing together what happened in those mysterious moments before everything we see existed, searching for evidence like frozen quantum ripples and hidden gravitational waves. For many years, the Big Bang was seen as the definitive starting point, an excellent model for explaining how the universe evolved from a hot, dense state into the web of galaxies we see today. However, a massive problem remains at its very root. When you try to use the equations of general relativity to wind back the clock, you eventually hit a wall where the math no longer makes sense. As matter becomes infinitely dense and temperatures rise without limit, the equations break down. This isn't just a technical glitch, it shows that the standard Big Bang model doesn't actually explain how the world truly began. This point of failure is known as the singularity. But instead of imagining it as a real physical point, think of it as a giant warning sign screaming that our theories no longer work. Einstein's gravity is perfect for stars and galaxies, but at the unimaginably tiny scales where quantum effects take over, it fails. The singularity isn't a thing, it is the result of our model reaching its limit. The standard Big Bang model is less a theory of origins and more a theory of what happened after the first measurable moment. The trouble starts when we try to trace time back to the very earliest slice of existence. At that extreme limit, density and gravity are so intense that quantum mechanics and gravity become entangled in ways we don't yet understand. General relativity views space as smooth, but quantum mechanics suggests that at tiny scales, space might be grainy or made of discrete units. Applying smooth geometry to this grainy reality gives absurd answers, like infinite density, which cannot exist in the real world. People often misunderstand the Big Bang as an explosion at a point in space, but it wasn't an event happening in space, it was space itself growing larger everywhere at once, with no center and no edge. The failure of our equations at this starting point is the strongest hint we have that we need a new theory, a quantum gravity that unites the smooth curve of the cosmos with the uncertainty of the microscopic world. Without it, we cannot see past the wall. Some models suggest the universe never actually reached a singularity. Instead, it might have experienced a big bounce, where a previous universe collapsed and rebounded. In this view, the singularity disappears, replaced by a smooth transition from an older era into our current expanding one. In those first fraction of a second after the beginning, the universe did something extraordinary. In a flash faster than the speed of light, the very fabric of space was stretched, dragging everything along in a sudden, violent growth known as inflation. Without this brief but dramatic phase, the structures we see today, galaxies, stars, and even ourselves, might never have formed. Inflation was proposed to solve deep puzzles that the basic Big Bang model couldn't answer. For instance, why is the universe so consistent in every direction? Even areas billions of light years apart have nearly the same temperature, yet they are too far apart for light to have ever traveled between them to share energy. Inflation solves this by suggesting that before the Great Expansion, the universe was tiny, and all its parts were close enough to reach a balanced temperature. Then, in an instant, that uniform patch was stretched to a cosmic scale. This also explains why space appears so flat. Just as the surface of a balloon looks flat if you zoom in enough, the rapid stretching of inflation smoothed out any curves or wrinkles in space. Most importantly, inflation acted as a cosmic gardener. During that rapid growth, tiny quantum fluctuations. Small shivers of energy were stretched into massive scales, creating the SLI. But what actually triggered this expansion? Theory suggests that the early universe was filled with a mysterious energy field, often pictured as a ball perched precariously at the top of a hill. As long as the ball stayed at the top, its energy drove that exponential growth. Eventually, the ball rolled down to a lower energy state, releasing its stored energy in a process that heated the universe and filled it with particles and radiation. This means that the hot Big Bang most people imagine actually happened after inflation ended. In a span of time smaller than can be imagined, the universe grew from something smaller than an atom to something far larger than everything we can currently see. The big question remains, what put that energy there in the first place? Some suggest that inflation is a natural property of space at high energies and might never truly stop, constantly creating pocket universes in a vast multiverse. Scientists are now searching for the fingerprints of this event, primitive gravitational waves that would have left a unique pattern in the oldest light in the sky. Detecting these ripples would be like hearing the faint echo of the universe's first scream. While we haven't found a definitive signal yet, new experiments are closing in. We are moving closer to understanding whether the universe began with a sudden spark or if it was always there, waiting in a quiet, stable state before it finally burst into life. Instead of a sudden explosion from nothing, the universe may have existed in a timeless, near-static state for an eternity, acting much like a cosmic egg. In this scenario, the Big Bang was not an absolute beginning but a phased transition, similar to water suddenly turning into steam. The universe waited in this stable state until a specific quantum fluctuation triggered a rapid and massive growth. Other models push this idea even further, suggesting that our universe did not start at all, but rather bounced from a previous state. Loop quantum cosmology replaces the dreaded singularity with a bounce. It describes a universe that contracted to a tiny, finite volume before quantum effects forced it to rebound and expand into the Big Bang we observe today. In this picture, there are no infinities and no breakdown of physics, only a new chapter of space-time governed by the laws of the very small. This model is built on the foundation of loop quantum gravity, which attempts to unite Einstein's smooth relativity with the grainy reality of quantum mechanics. While general relativity treats space like a perfectly stretched fabric, this quantum view reveals that at the smallest scales, space is made of discrete, atomic-like units. You cannot divide space forever, eventually, you hit its fundamental building blocks. This granular structure of space changes how gravity behaves under extreme conditions. Normally, gravity is always attractive. The more mass you cram into a space, the harder it pulls. But at the incredibly high densities of the early universe, these quantum units of space resist further compression. Loop quantum cosmology predicts that when the density reaches a critical threshold, quantum effects generate a powerful repulsive force. This isn't just a minor correction, it is a total reversal of roles. This quantum push is strong enough to stop the collapse entirely. The universe never reaches zero volume or infinite density, instead, it slows to a stop at a minimum size and begins to expand again. This bounce implies that time is continuous and has always been flowing. Before our current era of expansion, there may have been a previous universe that slowly collapsed until it hit the quantum limit, triggering our own birth. This model is attractive because it removes the mathematical nightmare of the singularity while keeping the laws of physics valid. Throughout the entire process, numerical simulations show that the energy density is capped at a maximum value, and the curvature of space-time never becomes infinite. The mathematics behind this big bounce treats space-time as a network of finite areas and volumes that evolve in discrete jumps rather than a continuous flow. This discreteness is what provides the strength to resist the collapse. But can we find proof of this today? Since the bounce removes the starting point, it might leave subtle fingerprints in the cosmic microwave background, the oldest light in the sky. Some models predict slight deviations in temperature and polarization patterns on the largest scales, or even unique gravitational wave signals that differ from those of a standard Big Bang. Detecting these signals would be a monumental step toward proving that a pre-Big Bang era actually existed. Although this theory is still being refined, it offers a robust alternative to a universe that begins with an impossible point. Regardless of the specific details of the previous universe, the math suggests that once density approaches the quantum limit, a bounce is inevitable. Beyond the bounce, the emergent universe model tells a different story. Here, the universe did not begin with a burst or a bounce, but was once incredibly calm, existing in a stable state for an infinite time before it finally began to grow. This cosmic egg sat in a near-eternal balance until a spark of energy, perhaps a scalar field rolling down a hill, triggered the expansion. This solves the problem of why the universe is so uniform, because it existed for an eternity before The emergent universe model offers a compelling way to bypass the philosophical dilemma of the origin of time, which is a central challenge in modern cosmology. A true beginning of time is difficult to express within the framework of cause-and-based science, but if time never truly started, the principle of causality remains intact. In this view, there is no first moment. Instead, the universe transitions endlessly from one phase to another. We may even be able to test this idea, as emergent scenarios leave potential marks on the largest scales of the cosmic microwave background. Because the universe remains static for so long, some models predict specific patterns, such as a slight suppression of temperature fluctuations or unique imprints from the pre-expansion state, which would differ from the signals expected from a sudden singularity or a quantum bounce. Furthermore, some versions predict a level of primordial gravitational waves much lower than what standard inflation suggests, providing a key way to distinguish between these rival origins. Beyond the bounce and the cosmic egg lies the ekpyrotic universe, one of the most ambitious ideas in cosmology. Instead of a singularity, it proposes that our universe was born from the collision of two high-dimensional branes in a larger space. This violent impact didn't happen in a void, it occurred in a world with extra dimensions, as described by string theory. When these two sheets of reality collide, they release a massive amount of energy, heating the region and triggering everything we call the Big Bang. The word itself comes from the Greek for cosmic fire, a fitting name for a model that replaces a mysterious explosion with a cataclysmic meeting that ignites the universe with matter and radiation. Crucially, in this scenario, there is no true first moment. These branes existed before the collision, and in some versions, they collide repeatedly, creating a cyclic universe with an infinite history of rebirth. This is rooted in higher dimensional physics, where our three-dimensional world is just one membrane floating in a broader space. As these branes slowly approach each other over eons, their movements are nearly imperceptible until the moment of contact, which converts their kinetic energy into the hot, dense plasma that fills our cosmos. This solves the problems of uniformity and flatness without needing a period of faster-than-light expansion, as the slow contraction before the crash naturally irons out any wrinkles in space. If the ekpyrotic idea sounds bold, the cyclic version takes it even further. Here, there is no beginning or end, the universe undergoes an endless sequence of contraction, bounce, and expansion. Each cycle clears away the remnants of the previous one, allowing the universe to reset and begin anew. From this perspective, the Big Bang is not a unique event but just the latest beat in an infinite cosmic rhythm. This model cleverly avoids the problem of entropy buildup that haunts other cyclic theories. By using dark energy to stretch space until it is nearly empty at the end of each cycle, it dilutes the disorder, leaving a smooth patch of space to start the next round without violating the laws of thermodynamics. It offers a vision of time that extends forever into the past and future, with the Big Bang being just one of many. While testing this is difficult, it predicts a very weak background of gravitational waves and specific subtle patterns in the ancient light of the universe that future experiments might finally detect. Even the flaws of the original model have been refined by newer theories, such as ghost condensation bounces, which use exotic fields to ensure the transition from collapse to expansion is smooth and stable, avoiding the chaos that usually accompanies such a massive reversal. One of the most creative ideas regarding what came before the Big Bang is Roger Penrose's conformal cyclic cosmology. He proposes that our universe is just one in an endless series of eons, each ending and smoothly transitioning into the next without a sudden halt or a point-like start. The key to this theory is conformal geometry, a mathematical tool that allows the distant, fading future of one universe to be seen as the hot, dense beginning of another. Penrose argues that in the far, far future trillions of years from now, when stars have died and black holes have evaporated, the universe will consist only of massless particles. When everything becomes massless, the very concept of a physical scale or a ruler disappears, and time loses its traditional meaning. In this cold, ultimate state, the geometry of space can be mathematically reshaped. By ignoring absolute size and focusing only on shapes and angles, the infinite stretching of a dying universe can be transformed into the smooth, concentrated start of a new one. In this light, our Big Bang may simply be the conformal recycling of a previous universe's icy end, a seamless bridge between an old world and a new dawn. This infinite process implies that each cosmic age, or eon, expands and fades only to give way to the next. One of the boldest claims of conformal cyclic cosmology is that information might actually survive the transition from one eon to another. Roger Penrose suggests that the final evaporation of supermassive black holes at the end of a universe could leave a faint fingerprint in the cosmic microwave background of the next. He and his collaborators claim to have found preliminary evidence in the form of concentric circular patterns with unusually smooth temperatures. These circles are theorized to be the remnants of high-energy events from a previous universe, echoing into our own. While some analyses claim to see these patterns, others remain skeptical, arguing that they might simply be random statistical fluctuations. The beauty of this model lies in how it avoids the need for a starting point or a quantum bounce. The universe naturally inherits its smoothness and flatness from the final, uniform state of the era that came before. However, the question of how matter loses its mass to allow for this geometric transformation remains a central mystery that physicists are still trying to solve. The idea that the oldest light in the universe holds clues to a previous world is a radical departure from standard theory. Penrose argues that these traces are not just random noise but a specific signature of Hawking radiation from evaporating black holes in a prior eon. In the distant future of a dying universe, black holes are the last surviving structures. Over unimaginable spans of time, they eventually evaporate, releasing their mass as bursts of energy. As the old universe fades into its final smooth state, these bursts don't vanish, instead, they appear as slightly warmer circular regions at the dawn of the next age. Because there would be many such black holes, these signals would overlap, creating the low-variance concentric rings predicted by the model. While the Penrose team reports finding dozens of such rings in satellite data, independent groups have countered that these patterns could be coincidences within such a vast sky. This debate remains one of the most exciting frontiers in cosmology, as the next generation of experiments may finally provide a definitive answer. If these rings are real, the Big Bang was not the beginning, but a rebirth. Another profound possibility is that our universe was born not from a void, but inside a black hole from a parent universe. This is the black hole bounce or fecund universes hypothesis. It suggests that the extreme environment at the core of a black hole doesn't lead to a dead-end singularity, but triggers a bounce that gives birth to a new cosmos. While general relativity predicts a breakdown of physics at the center of a black hole, quantum gravity suggests a different fate. As matter falls into a black hole and density approaches a critical limit, a repulsive quantum force takes over, reversing the collapse into a rapid expansion, a mini Big Bang within the event horizon. From the outside, we only see a black hole swallowing matter, but on the inside, a whole new universe could be flourishing. In this cosmic tree model, every black hole in every universe could be a gateway to a new branch of reality. This provides a natural explanation for what happened. Before the Big Bang, time didn't start at a point, it continued through the event horizon of a black hole in a mother universe. If black holes can lead to new universes, what does that transition actually look like? The white hole transition hypothesis extends this idea by proposing that the collapse inside a black hole eventually turns inside out, transforming into a white hole that ejects matter and energy into a new region of space-time. In this scenario, the black hole is not an eternal prison but a one-way tunnel. While white holes are allowed by Einstein's equations, they have never been observed in our own sky. However, in the context of quantum gravity, they become the potential birthplaces of universes. As matter is crushed to extreme densities, quantum effects stop the collapse and push it back out, creating a massive explosion of energy similar to the conditions of our own Big Bang. This transition offers a way to preserve information, as anything that fell into the black hole could eventually escape into the new universe. This also explains why our early universe was so uniform. The extreme compression before the bounce would have smoothed out any irregularities, leaving the white hole to start the new cosmos with a clean, orderly slate. While testing this is difficult due to the time dilation near black holes, scientists are looking for exotic energy bursts in our own universe that might be the signals of ancient black holes finally making their transition. At a more macroscopic level, patterns in gravitational waves or the peculiar distribution of large-scale matter might hint at a white hole origin for our cosmos. One fascinating idea is that if our universe was born from a bounce or a cycle, not everything was erased in the transition. Certain structures, particularly black holes or their quantum remnants, might have crossed the threshold into our universe to drift silently as dark matter. This concept stems from the theories of loop quantum cosmology and the bouncing universe. During a bounce, while densities are extreme, they remain finite, allowing some supercompact objects to survive. While most matter and energy are redistributed, black holes below a certain mass or their Planck scale cores might be stable enough to endure. Their event horizons might shrink, but they wouldn't vanish. As the universe enters its new phase, these ancient relics interact with the new cosmos only through gravity. This offers several elegant solutions. It removes the need for unknown new particles to explain dark matter. It explains why dark matter has no electromagnetic interaction, and it matches the observed mass scales we see in galaxy rotations. Detecting these relics is a challenge, but not an impossible one. We can look for them through microlensing events, where an invisible compact object briefly brightens a distant star as it passes in front of it. Additionally, if larger black holes survived from a previous age, they might have acted as the seeds for the supermassive black holes we see at extreme redshifts, solving one of the greatest mysteries in modern astronomy. Is it possible that dark matter didn't just appear after the Big Bang, but existed long before? New research suggests that dark matter may have formed before our visible universe took shape, leaving a hidden imprint on today's cosmic structures. If true, dark matter is not just a modern puzzle, but a legacy from a different phase of the cosmos. While standard cosmology suggests dark matter condensed from particles after the Big Bang, alternative theories propose it was born during a prior contraction or even within a timeless state before the expansion began. One attractive idea involves scalar fields, fundamental fields that can exist even in empty space. Through a process called freeze-in, dark matter particles could have been generated so slowly and weakly that they never reached thermal equilibrium with the rest of the universe. This could have happened during the inflationary period or even earlier. These pre-Big Bang particles would be nearly invisible to our direct detection experiments today, yet they would carry the correct density to explain the universe's missing mass. Because they were born so early, their distribution would subtly alter how galaxies formed over billions of years, providing us with a unique window into the physics that preceded the hot Big Bang. The oldest light in the universe, the CMB, is the ultimate hunting ground for what happened before the Big Bang. This ancient radiation, born shortly after the beginning, carries the signature of the early cosmos. Different pre-Big Bang models, whether inflation, a bounce, or a cycle, predict slightly different patterns in the CMB's power spectrum. For instance, while standard inflation predicts that fluctuations should look nearly identical at all scales, bouncing and cyclic models often suggest a suppression of power at the largest scales. Interestingly, satellite data does show a slight deficit of power at these massive scales, which has breathed new life into alternative theories where such suppression is a natural outcome. Another key clue lies in non-Gaussianity, tiny deviations from a perfect random distribution in the density of the early universe. In a simple inflationary model, these fluctuations are nearly perfect, but models involving a contraction phase or multiple fields tend to produce unique, non-random signatures. If we were to detect a significant non-Gaussian pattern in the CMB or the large-scale distribution of galaxies, it would be a major blow to standard inflation and a strong signal that our universe began with a much more complex mechanism, such as an ekpyrotic collapse or a quantum bounce. The precise identification of bispectrum shapes is set to become a powerful diagnostic tool in our exploration of the cosmos. Furthermore, the study of primordial four-point correlation functions is gaining significant traction. Even if the bispectrum signal remains faint, certain bounce and cyclic models predict much stronger features within these four-point functions. Gravitational waves originating from the very dawn of time may hold the key to clarifying the truth of what preceded the Big Bang. Unlike photons, which were heavily scattered before the era of recombination, gravitational waves have traveled almost entirely unimpeded from their source to the present day. They act as messengers from regions where light simply cannot reach. If we can detect them, we will finally be able to determine whether the early universe underwent a period of rapid inflation, a slow contraction, or perhaps a quantum bounce. In the standard inflationary paradigm, the sudden stretching of space would amplify quantum fluctuations of gravity, generating a nearly scale-invariant spectrum of gravitational waves. These would leave a unique signature known as B-mode polarization on the cosmic microwave background, or CMB. This intensity is often quantified by the tensor-to-scalar ratio, and while different inflationary models offer various predictions, no conclusive detection has been made to date. The BICEP2 collaboration once claimed a discovery of B modes, but this was later identified as contamination from galactic dust. Current upper limits from missions like Planck and BICEP/Keck have already ruled out many high-energy inflationary models. While no signal has been detected yet, this has not only narrowed the parameter space for inflation, but also opened the door for alternative theories. Bounce and cyclic universe models generally predict much weaker or even non-existent primordial gravitational waves. In frameworks like loop quantum cosmology or the ekpyrotic scenario, the slow contraction preceding a bounce strongly suppresses tensor perturbations. If the early universe was dominated by contraction rather than inflation, the resulting gravitational wave production would be incredibly minute, a critical point of divergence between these theories. If future CMB experiments continue to push sensitivity boundaries without finding a signal, the evidence will increasingly favor bounce and cyclic models. However, not all bounce scenarios are silent. Some versions of the matter bounce predict a blue-tilted gravitational wave spectrum. This stands in stark contrast to the red-tilted spectrum predicted by inflation on large scales. Observing a blue-tilted spectrum in specific frequency bands would serve as a smoking gun for a bounce rather than inflation. Furthermore, some ekpyrotic models might produce unconventional polarization patterns or frequency-dependent signals that are distinct from the smoother inflationary background. The conformal cyclic cosmology, or CCC, offers an even more unique perspective. It does not anticipate a strong inflationary-like gravitational wave background but suggests that other gravitational traces of the distant past might remain. For instance, the evaporation of supermassive black holes at the end of a previous eon could produce bursts of gravitational radiation. In the CCC framework, these might appear as subtle anomalies in the CMB, potentially linked to what are known as Hawking points. To capture these elusive signals, experimental precision is reaching new heights. Projects like Lightbird and CMB-S4 aim to push the detection threshold for the tensor-to-scalar ratio down to approximately 0.001. If they discover a clear inflationary signal, it will provide massive support for the Big Bang. If not, the result is still a profound victory for science, providing strong evidence for bounce and cyclic models where tensor modes are suppressed. Looking further ahead, instruments like LISA, DISIGO, and the Einstein telescope will search for primordial gravitational waves directly across different frequency bands. Some bounce models shift their power into frequency ranges beyond the CMB, falling right into the sensitivity windows of these future instruments. For example, a blue-tilted spectrum at the megahertz level might be detectable by LISA. The CMB is often celebrated for its nearly perfect fit with the standard model, yet a closer look reveals several persistent anomalies. These could be mere statistical coincidences, or they might be the first clues of pre-Big Bang physics. Among the alternative models, CCC stands out because it directly predicts bizarre patterns, the most controversial of which are concentric circles of low variance. If confirmed, these would provide powerful evidence that our universe had a history before the Big Bang. While the standard inflationary expectation is a Gaussian random distribution of temperature fluctuations, the WMAP and Planck maps have shown outliers, such as the hemispherical asymmetry and the cold spot, which are difficult to explain without invoking rare coincidences. CCC interprets these features as natural relics of a previous eon. The most direct prediction is the existence of these concentric circles in the CMB. Sir Roger Penrose's team reported finding dozens of such circles in the data, suggesting areas where multiple black holes evaporated sequentially. Since no inflationary model predicts such structures, the news caused a sensation. However, controversy followed, as independent teams pointed out that the statistical significance might have been overestimated, noting that random CMB simulations can occasionally produce similar-looking rings. Furthermore, these rings, if they exist, might stem from unknown astrophysical foregrounds rather than a prior universe. Despite this, the Penrose team continues to claim the detection of Hawking points in updated data, though independent confirmation remains elusive. Beyond these circles, CCC also provides a natural explanation for the lack of power at the largest angular scales. Since CCC does not rely on inflation, it allows for the suppression of fluctuations at these scales, which matches the observations from the Planck satellite. Future CMB measurements will be vital. Lightbird and CMB-S4 will revisit the entire sky with lower noise and higher resolution. If the low variance circles and Hawking points withstand rigorous testing, the credibility of CCC will rise significantly, potentially challenging inflation as the best explanation for the early universe. One of the greatest contradictions in modern cosmology is the growing Hubble tension, the discrepancy between bang scenarios like the bounce or ekpyrotic models, scalar fields, or dark energy-like components active during the contraction phase might leave a residual footprint in the early expansion. This discussion has been further intensified by the James Webb Space Telescope, which discovered bright, massive galaxies forming much earlier than expected under the standard cold dark matter model. If these results hold, it may imply that the initial conditions of the early universe were extraordinary, hinting at complex events preceding the Big Bang. Some researchers use this to support bounce models or pre-Big Bang phase transitions. Loop quantum cosmology also offers a possible explanation, as the bounce modifies the Friedmann equations at extreme densities, subtly shifting the evolution of the universe in a way that might resolve the Hubble tension. CCC allows for residual gravitational effects from the previous eon to subtly alter large-scale structures, indirectly influencing our inference of the Hubble constant. Verifying these ideas requires cross-generational validation. If new early universe physics is causing the tension, we should see corresponding deviations in other parameters, such as the acoustic scale or baryon acoustic oscillations. Surveys like DESI are currently mapping the large-scale structure of the universe with unprecedented precision to discern whether the tension is a systematic error or evidence of physics beyond the standard model. We can also look for clues in CMB lensing signals and galaxy cluster distributions. If scalar fields from a contraction phase or early dark energy influenced expansion, they would leave traces in the clustering patterns on the largest scales. To truly understand what happened before the Big Bang, we need a three-dimensional map of the cosmos that shows both its current state and its past evolution. Cutting-edge projects like SPHERX and DESI are powerful tools for this task. SPHERX, a NASA mission, will conduct an all-sky spectroscopic survey, measuring the spectral signatures of hundreds of millions of galaxies across a wide range of redshifts. This will allow for the construction of a massive 3D map to test whether the standard expansion history holds or if it aligns better with scenarios involving early dark energy or a bounce. SPHERX will also test inflation by measuring the non-Gaussianity of galaxy clustering. If the large-scale structure is nearly perfectly Gaussian, it supports standard inflation. Any subtle anomaly might suggest the involvement of a pre-Big Bang phase. Meanwhile, DESI is already focusing on millions of galaxies and quasars to characterize the expansion history in unprecedented detail. By pinning down the evolution of the expansion rate, DESI can indirectly test for the presence of evolving dark energy, which is a common requirement for bounce and cyclic models. If DESI's data continues to show inconsistencies between early and late expansion, it will add weight to the theories of physics beyond the standard model. Dark energy itself remains one of the greatest mysteries in cosmology. If it is not a constant but evolves over time, it would not only rewrite the future of the universe but also reveal its past. In evolving dark energy models, the acceleration is not constant, the strength and equation of state can change, potentially turning from a repulsive force to an attractive one in the distant future, triggering a transition from expansion to contraction. This is essential for the rhythm of cyclic universes. In ekpyrotic models, dark energy plays a dual role. It smooths out space-time today, but over vast time scales, its nature may change, allowing gravity to regain dominance and lead to a new bounce. Without evolving dark energy, this cosmic heartbeat would be impossible to orchestrate. Some loop quantum cosmology scenarios also predict unconventional dark energy behavior near the bounce, where it might couple with quantum geometric effects. This means dark energy might not just be a late-stage phenomenon, but a fundamental driver of cosmic dynamics from the very beginning. Ultimately, the behavior of dark energy determines whether our universe is a one-time event or an eternal cycle. As future surveys like DESI and Euclid measure the expansion rate across different epochs, any deviation from a constant value will provide massive support for the existence of pre-Big Bang physics. The dynamic component of dark energy might very well be the metronome governing the cosmic phase transitions of our universe. Even within the Big Bang camp, physicists are beginning to wonder if the dark energy we observe today is linked to the primordial inflation field, perhaps a lingering remnant of a scalar field that existed before the Big Bang itself. This leads us to the ultimate question: what is the final fate of our universe? Will it expand forever until it becomes a cold, desolate void? Will it reverse course and collapse under its own weight? Or is it part of an eternal cycle of contraction and rebound? These scenarios, the Big Freeze, the Big Crunch, and the under the standard lambda cold dark matter model, if dark energy remains a constant force, the universe's fate is the Big Freeze. In this scenario, the acceleration never ends. Trillions of years from now, galaxies will recede from one another at apparent speeds exceeding that of light. Stars will flicker out, black holes will evaporate through Hawking radiation, and the universe will dissolve into a dilute soup, a dark vacuum of low-energy photons and stray particles where time continues, but nothing ever happens again. While bleak, this path aligns remarkably well with current observations. However, if dark energy evolves, weakening or even reversing its sign, gravity could regain control, leading to the Big Crunch. In this version, expansion slows, stops, and reverses. Galaxies collide, and the universe shrinks into an ultra-hot, ultra-dense state. While classical general relativity suggests this ends in a singularity, theories like loop quantum cosmology and the new ekpyrotic model suggest that the singularity is replaced by a bounce. This big bounce occurs when the universe contracts to near Planck density, where quantum gravitational effects create a repulsive force that prevents an infinite collapse. The universe reaches a minimum scale and then expands once more. In this light, the Big Crunch is not an end, but a transition, a node in an eternal rhythm of contraction and expansion. This doesn't just rewrite our future, it rewrites our history. If a bounce can happen in the future, it likely happened in our past, meaning our Big Bang may have been the most recent bounce in an infinite series. While each cycle erases most evidence of the previous one, subtle imprints such as large-scale power suppression or specific gravitational wave signatures might still remain. The ekpyrotic cyclic model takes this further, suggesting that periods of slow contraction smooth out irregularities without the need for an absolute beginning. Whether our fate is a lonely freeze or a rhythmic bounce depends entirely on the personality of dark energy. Missions like Euclid and the Vera Rubin Observatory are now tasked with determining if dark energy evolves, a discovery that would point directly to the true nature of our cosmic past. For a long time, the cosmic microwave background, or CMB, has been the gold standard for testing these theories. Its alignment with the standard model is a triumph of science, Yet as our observations sharpen, new anomalies are challenging the narrative. Some of these discrepancies may point to deeper physics or pre-Big Bang processes. For instance, the James Webb Space Telescope has discovered bright, massive galaxies in the ultra-early universe that seem to have formed much faster than the standard model predicts. If confirmed, this suggests that early density fluctuations were stronger or fundamentally different than we thought. Since these fluctuations are etched into the CMB, any deviation points toward different initial conditions, perhaps those predicted by bounce or cyclic models. Furthermore, as we try to strip away foreground noise from stars and dust to see the pristine CMB, we are finding that early star-forming galaxies might be contaminating our measurements. This raises a critical question: are the contradictions in our models merely data interpretation errors, or are they genuine signals of new physics, like traces of a pre-inflationary phase? Beyond the mainstream, there are more exotic ideas, such as the hypothesis of Sala particles. This controversial view suggests the Big Bang was triggered by interactions between pre-existing exotic particles rather than a singularity. While not widely accepted, proponents argue these subphotonic building blocks existed in a superstable, zero-entropy fluid before the Big Bang. An instability in this fluid supposedly released the energy that ignited our universe, with remnants of this field potentially explaining dark energy or dark matter today. Similarly, plasma cosmology once proposed a universe shaped by electromagnetic forces rather than gravity, avoiding a Big Bang altogether. However, modern evidence has largely moved past this. The near-perfect black-body spectrum of the CMB and the observed abundance of light elements are natural results of a hot Big Bang that plasma theories struggle to replicate. Ultimately, modern cosmology has achieved brilliance, but massive gaps remain. The singularity problem persists because our current laws of physics break down at the very beginning. We still don't know what ignited inflation, what dark matter actually is, or why the Hubble constant shows tension between early and late universe measurements. These mysteries leave the door wide open for pre-Big Bang physics. Whether the universe began with a singular flash, a quantum transition, or is an endless heartbeat of bounces, we are still searching for the definitive fingerprint. As we refine our maps of the cosmos, we move closer to understanding if we are living in a unique moment of creation or an eternal cycle. That is all for today's deep dive into the foundations of our reality. Wishing you wonderful dreams and a beautiful day ahead. Until next time.